this talk, I will not talk about MySQL, MongoDB, etc. So I'll talk about Cassandra. So I'm here to share with you an interesting project we have been working on since last year to improve the Apache Cassandra database, improve the performance significantly by building a new storage engine on top of RocksDB. So my talk is divided into 4 parts. Firstly, I will talk about the motivation and the background of this project. Secondly, I will go through different approaches we considered and the overall design of the whole project. The last part is the most interesting part. I will share with you the performance metrics in our internal deployments and also on AWS environment. To many people, Instagram is a branch sharing app. It started in October 2010 and has grown worldwide to be one of the largest visual media social platforms. Today, there are more than 800 million monthly active users shared their lives on Instagram. So you can tell a story of your life on Instagram. You can communicate visually with your friends and family on Instagram. You can also go live on Instagram and explore just about anything. So you may be wondering what are the technologies behind all these cool features. So at Instagram, besides leveraging Facebook infrastructures, we also use a lot of open source technologies. And Apache Cassandra is the key value data store we are heavily using at Instagram. Let's take a look at what are the features provided by Cassandra. So you may know Cassandra is a highly scalable partitioned data storage. It provides high performance, especially for write-heavy use cases. It uses peer-to-peer architecture so that it can provide high availability with no single point of failure. It also provides tunable consistency, so you can specify the consistency level you want per request. At Instagram, we have one of the largest Cassandra deployments in the world. So we're running thousands of Cassandra servers across multiple data centers, serving hundreds of product use cases with millions of QPS. Also at Instagram, most of the Cassandra requests are online requests. So we need to, in order to provide a reliable and responsive user experience for hundreds of millions of Instagram users, we have a very tight SLA on Cassandra metrics. So we maintain a 5 nines Cassandra reliability SLA, which means at any given time, the request failure rate should be less than 0.001%. We also care about the performance a lot. We actively monitor the throughput and the latency on different Cassandra clusters, especially the read latency. So we have been doing a lot of tunings to lower down Cassandra's latency, but there is still a lot of room for improvements. Let's take a look at latency on one of our product clusters. So this is a Cassandra cluster serves critical data for Instagram users. It serves both high read throughput and also high write throughput. As you can see, the orange line is the Cassandra P99 read latency, and the blue line is the average read latency. So the average one is as good as 5 milliseconds, but in the P99 read latency, it has a long tail. It varies from 25 milliseconds during the night to 60 milliseconds during the peak time. So you can see the latency is not consistent, and the gap is very high. So we want to continuously lower down the P99 read latency, which could leave more room for our product engineers to show better features to our users. We investigated a lot to figure out why the latency is so high, and this graph is very interesting to us. As you know, Cassandra is a database written in Java. So unavoidable, we need to pay the price for JVM overhead. So how much price did we pay? It is surprisingly high. So this is the GC store graph we collected from the Cassandra servers in the same cluster. So it shows what's the percentage of time the JVM is doing stop or the GC and cannot serve user request. So from this graph, you can see the Cassandra server has from 1% to 2.5% of the time it is doing the stop or the GC. This actually proved to be the biggest impact to our P99 read latency. So we want to reduce the GC stores as much as possible. What can we do? We consider the different approaches. So the first one we considered is to, obviously to do more GC tunings. So JVM provides a lot of tunable parameters. We can play with different settings, for example, try to reduce the number of objects being copied to the origin, and try to reduce the GC execution time, which will improve the performance for our Java service. So for this approach, the pros is that there's no Cassandra code change needed. But there are many challenges as well. As you see, Java has so many parameters to tune, and we need to tune them for both low latency and high throughput. Even worse, the JVM behavior highly depends on different workload. So, which means there's unlikely to be one set of parameters can work well for all different workloads. So we need to tune the parameters per use case. And also we already, did a lot of JVM tunings, and already got a large portion of P99 read latency job. So it is becoming harder and harder to reduce the latency further. We expected maximum about 20% of latency job for future tunings, which is not enough to us. So we start to look for different options. The second approach we considered is to move different Cassandra data structures to be off-heap, so that we can bypass the JVM and manage the memories by ourselves. So here are a list of data structures which generates a lot of objects in the JVM and cause a lot of pressure. So if we can move all this, or majority of these components to be off-heap, we should be able to reduce large portion of the JVM overhead. So for this approach, the pros are, there are incremental improvements. We can get X% of gains by converting each data structures to be off-heap. And potentially, they are easier to be contributed back to the Cassandra community. The challenges are we need to play with Java unsafe, which can be error-prone. And also, for a lot of data structures and components, the current logic are complex. They're not, the code is not structured in a way that keeps objects recyclable in the mind. So it is non-trivial to reflect existing logic as well. And also, there are always new features, new code coming every release, which means we need to always play the catch-up game. So since we know majority of the JVM overhead comes from the storage engine part, like the mem table, compression, etc., then a bold idea comes into our mind. Why not we switch the existing Java storage engine to a new C++ based implementation, so that we will get rid of majority of the garbages created in JVM, which also means we will make the Cassandra storage engine to be pluggable. So this is the third approach. The pros are, we can greatly reduce the JVM overhead. And potentially, we can get more CPU efficiency by using more C++ in the critical paths. And also, we believe we can get long-term benefit from the pluggable storage engine architecture in Cassandra. So for the challenges are, currently, the Cassandra storage engine is not pluggable, which means the storage engine is highly coupled with other components, like streaming, like repair, etc. So we need to spend a non-trivial effort to refactor the Cassandra code base to make the storage engine to be pluggable. And also we plan to use GenI as a bridge between the Java and the C++, So we need to be very careful about the efficiency and the reliability of the GenAI interface. After we considered all the three options, we think the third option has the biggest potential, and it is the correct direction we want to move towards. So we investigate more into the third option, which is the C++ storage engine option. We did not want to build a new C++ storage engine from scratch, so we're looking for existing solutions. Then, and RocksDB comes into our picture. So as you may already know, RocksDB is the open source, high performance embedded database for key value data. It is written in C++ and has official API bindings for like C++ and Java. And also, like as I said, RocksDB is optimized for performance, especially on fast storage like SSD. And also, it is widely used in the industry as the storage engine for MySQL, MongoDB, etc. So we decided to try to build the new storage engine on top of RocksDB. To prove the concept, we built the prototype, which injected RocksDB into Cassandra for a single key value use case, which means like we bypass the Cassandra's own storage engine, converted Cassandra's query into RocksDB's API call, and pass the Cassandra request to RocksDB instance through the RocksDB GenAI interface. After we finished the prototype, we shadowed one of our product use case. So let's take a look at the latency result of the prototype. So the blue line is the Cassandra 3.0 cluster P99 read latency. And the red line is the Cassandra on RocksDB cluster P99 read latency. Again, both are measured from our web server, which is the client of the Cassandra cluster. So as you can see, the RocksDB-based cluster, the P99 latency is constantly below 5 milliseconds. But for the Cassandra 3.0, it varies from 15 milliseconds to 35 milliseconds. So you can see it's 6 times reduced during the peak time. And then we looked at the GC stores as well. Again, the blue line is for Cassandra, and the red line or orange line is for the Cassandra on RocksDB. So you can see the Cassandra GC store varies from 0.5 to 1%, but for the RocksDB-based cluster, the GC store is constantly below 0.1%. So it's a 10 times drop of the GC store during the peak time. So this gave us a lot of confidence of the project, and we decided to move forward with this option. So we choose to build the storage engine on top of RocksDB, and we named the project like Cassandra. After we finalized the design, there were two main challenges we need to overcome during the implementation. The first one is how to convert Cassandra's data model on top of RocksDB. The second is to support Cassandra streaming. Let's talk about the data model first. Cassandra uses wide column data model, which means in a table, there are multiple columns in a row. So among all the columns, the first column is defined as partition key, which is used to distribute the data across all the nodes in the cluster. Then there could be one or multiple columns defined as clustering key. So the clustering keys are used to order the data within one single Cassandra server. The rest of the columns are just normal cells. On the other hand, RocksDB uses a much simpler data model, just from blob key to blob value in bytes order. So we need to encode the Cassandra's, the wide column data model onto RocksDB. So we divided the challenge into two parts. So first, we deal with the key encoding. The first requirement for key encoding is to keep the same sorting order of Cassandra rows in RocksDB. so that range query works. So we encoded Cassandra's partition key together with all the clustering keys into RocksDB's key part to meet this requirement. It is not a simple concatenation because we need to support different key types, like integer, long, text, even blob. We need to play like bits manipulation games so that like the encoded key will have the same sorting order as the original data type in Cassandra. So this will make the range query in RockSandra returns the exact same result as the original Cassandra. So our encoding are mainly based on an open source library called Orderly. And we added some data type extensions which Cassandra needs. So the next part of the data model support is the value encoding. So besides encoding multiple cell values, we also need to encode the timestamp, TTL, deletion information, etc., along with the value. So we designed a special format to hold all this information and write C++ components for serialization and deserialization. And on top of that, we wrote a customized RocksDB merge operator and a compression filter in C++ for merging different versions of data based on the timestamp, and also for handling the purge of experiment data, based on the tombstone, TTL, GC grid seconds, etc. Besides the data model, another big chunk of work is the streaming support. In Cassandra, like it is a distributed database. So whenever we add a new node into the cluster or remove existing node out of the cluster, we need to stream data among different servers to balance the load across the cluster. And currently, the Cassandra streaming is based on transferring the underlying SS table files, which does not work on top of RocksDB. We ended up using RocksDB's iterator to scan and transfer data from the source servers. And on the destination nodes, we use the SS table writer of RocksDB to write the data into temporary files, and then ingest them into RocksDB in a batch way. So we measured that we can get more than 100 megabytes per second streaming throughput, and it is good enough for us. So after about 6 months of development and testing, we hit our feature milestone. So with all the implement features, we are able to support most of the use cases in Instagram. So since late last year, we started to roll the RockSandra out into our production clusters. The first cluster we converted already had very low read latency, but we did enjoy the throughput increase so that we can reduce the footprint to be 1/3 of the original footprint with the same low read latency. For the second cluster we converted, we got 3 times read latency drop from 60 milliseconds to 20 milliseconds for P99. And this is, and we also reduced the footprint to 60%. For the third use case, it's a very interesting use case. It has very high read throughput and also large fan-out read throughput. So with the original Cassandra 3.0, we cannot make it work unless we throw a large amount of machines into it. The GC store was higher than 5%, and the latency, the P99 latency was higher than 1 second on the client side. So after we converted it to RockSandra, like we are able to reduce the GC store to less than 0.1%, which translated to like 100 times latency drop on the client side from 1 second to 10 milliseconds. Besides internal deployments, we also want to verify whether Cassandra can work well in public cloud environment. So, and also to let everyone in the community can reproduce the benchmark, we set up the AWS benchmark environment and use the open source NDBench tool to do the testing. This is a benchmark result for a workload contains 30,000 read QPS and 30,000 write QPS. It compared the average P99 and P99 read latency. So the blue one is the Cassandra 3.0 cluster, and the orange one is the Cassandra, the RocksDB cluster. As you can see, the RocksDB cluster can provide 2 times lower P99 read latency and about 20 times lower P99 read latency. And similarly, this is the graph for write latency. RocksDB can provide 4 times lower P99 write latency and about 25 times lower P99 write latency. We also tested read-only workload. This is the graph shows the relationship between the P99 read latency and the throughput. As you can see, RocksDB can provide much higher read throughput with more consistent P99 read latency. And similarly, with this is a graph shows the relationship between the P99 read latency and the throughput. Okay, as a recap, switch to the RocksDB helped us to cut down the tail latency and improve the throughput, make Cassandra's behavior to be more predictable and more consistent, and more efficient. So all our work are open source, so please do not believe just like what I said. You can download the RocksDB source code and the benchmark framework from our GitHub account, and you can run it by yourself and see the result. Our next stage of work will be focused on rolling Cassandra out to all Instagram Cassandra clusters and support more Cassandra features. We will also work together with the Cassandra community to make the pluggable storage engine to be pluggable, so that we can upstream our work to the community and more people can benefit from the improvement. Last but not least, I want to thank for all the support from the Cassandra community and also RocksDB community. Without your help, and we will not be able to achieve this. That's all. Thank you. What's the Cassandra compression? So at Instagram, we mainly use the level compression. We use the level compression as default, which is same as the compression we used in the RocksDB. Question, yeah.
So if I'm using time window compaction, I'm getting my results back there.
Yeah, we haven't tried the time window compression in Instagram yet. Yeah.
Also, did you evaluate SolarDB as well?
Yeah, I expect someone will ask about SolarDB. Yeah. Personally, I did not try SolarDB, but again, all our code are open source. So if you want to compare it with SolarDB, welcome to do that. And in the future, when we have more time, maybe we will also like try to benchmark with SolarDB. Yeah. Yeah. You mean backup restore? We preload about like I remember like 500 gigabytes data before before we run the benchmark. So which means like the data size is definitely bigger than the memory. So the P99 and the P99 should load the data from disk. So it's not cached in memory. How did we shadow, right? Yeah, so in Facebook, So first we use the Swift API of Cassandra, and also in Facebook, a lot of services are built around Swift. So we have a lot of infrastructure around Swift. So for example, like we have a kind of a proxy, we can just turn on like a traffic forwarding in the proxy, so that it can forward the production. It can duplicate the production traffic and forward one copy to the shadow cluster, so that we can kind of double read, double write into two clusters and measure the result. Yeah. Any questions? Okay, I guess it. We already roll out into our production. Yeah. Yes. So first, all our code base, all the Rocksandra code is public in the Instagram GitHub account, and we do plan to contribute back to the Apache mainstream in the future. Just as right now, we are focusing on make the Cassandra's own storage engine to be pluggable first, so that we can provide a separate storage engine implementation based on RocksDB, and later user can choose whether you want to use the original storage engine or use the RocksDB based storage engine for your key space for your table. Yeah, the Cassandra process is still running in JVM, so more or less there are still some garbages created in the JVM, but because we moved the storage engine to C++, which means almost no objects are promoted to origin, so which means all objects will be recycled almost all objects will be recycled in the new gen. And it is much easier for JVM tuning. We can set the parameters, optimize for the young gen, the young GC. Yeah. Yeah, but the GC store is very very minimum. Right now it's 0.1% compared to 1% or 2% before. Yeah. Okay, thank you everyone.